Hi everybody, Physics Ninja here. Today's tutorial is all about how do you calculate power. So what we're going to do is we're going to start by reviewing the key items related to how to calculate, for example, the average power. Other questions associated with power might be how do you calculate an instantaneous power given a particular problem. So I'm going to look at 3 different problems. All of the problems will involve calculating power. And in order to calculate power, you're going to see you have to have a good handle on how do you calculate work in physics. So lucky for you, I already did a video on how to calculate work in physics. So if you don't know that, I would go watch that video first. I'll post the link in the description down below, and then you'll be ready to calculate power. All right, like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It is the best way to support what I do. All right, let's get started. All right, before looking at the problems, let's look at some key points related to power. Here's a cartoon here, depiction of a situation. So I imagine I have a crate on the floor. I'm going to neglect friction for now. I tie a cable here to that crate, and I am simply going to pull on it. So I am going basically just drag that crate across the floor. And I'm going to drag it a certain distance x along this floor. All right, if you do a free body diagram now on this crate, well, it's pretty straightforward. You have an applied force or a tension force here in that cable that's connected to the crate. I'll just call it F. We have a normal force from the floor, and we also have the weight of the crate. Since there's no friction, there's no forces acting to the left. Well, let's look at some key characteristics of what's going on now. I do have a net force, right? So the crate is going to be speeding up because the net force in this case is simply this tension force, which equals to my applied force pulling on that cable. So that's very important to realize. Now, this force is actually doing work. If you remember the definition of work, if you have a force and a distance, and in this case they're in the same direction, right? The force and the displacement of the crate are in the same direction, we would say this force does positive work. All right, so what happens now? Well, if you have positive work, another way to consider that is that the energy of the crate is changing, right? It was, say, initially at rest, and now it's going to be accelerating, so it's going to speed up over that certain distance. And the last thing, the energy that we're talking about in this case is the kinetic energy, because we're only looking at motion along that horizontal axis here. But in this case, it's clearly the kinetic energy that is speeding up. All right, so how is this then all related to power? All right, we now start with a definition of power. Power is nothing more than the rate at which you change the energy, okay? So the rate of change of energy. And you think about the change of energy, that is also the definition of work in physics, okay? So you can write power then as being the rate at which work is being done. For example, work is being done by this force F acting on the crate, and it's being done at a specific rate. Now in physics, the way you write a rate is you can do it like this, all right? For example, for instantaneous power, this would be the power at any specific time. I could write this as P of T is you differentiate the work with respect to time. Okay, that is a definition of instantaneous power. I'm going to show you how to apply this equation to problems in the problem section of this video. Now we can also talk about average power, and average power is a little bit simpler because it doesn't have to involve this derivative right here. So for average power, all you have to do then is you look at the total work being done in a certain amount of time. Okay, so that work here in the numerator in my formula over here, this would be the total work done in that amount of time that we're looking at, delta T. So let's look at a specific examples just to highlight the difference here between average power and work. All right, since we have power in units or as a definition of work divided by time, well, work is a change of energy, so that would have to be measured then in joules, right? And our time, again, we're going to just work in seconds. So a joule per second is something we call a watt. Okay, and if you have several of them, we're going to have watts for our SI unit of power. Okay, you often read problems, however, where power is sometimes written in terms of different units other than the SI unit system. A common one is the horsepower. Sometimes it's abbreviated as HP for horsepower. You can easily convert from horsepower to watts using this simplification down here. 1 horsepower is approximately equal to 746 watts. All right, let's look at a simple example here just to illustrate the differences between work and power. I have the situation outlined in this little sketch down below. So I have 3 bricks. Each brick has a mass of 2 kilograms. And my goal is simply to lift the bricks and place them on top of this ledge, which is a distance of 1.5 meters above the ground. In the first case, I want to accomplish all of this in 15 seconds. Okay? I'm going to do it rather fast. And in the second case, what I'm going to do is, again, I'm going to lift the 3 bricks. I'm going to take my time, and it's going to take me a total time of 60 seconds. So in each case, how would you calculate the work? And then how would you calculate the average power? All right, so my work, in this case here, I have to do work in order to lift those bricks. The amount of work that this person does here, if the bricks started at rest and they end at rest, is simply going to be the change of potential energy of the 3 bricks. So I can easily calculate that. It's simply going to be 3 times because I have 3 bricks. And for each brick, it's simply the mass of the brick, little g, and multiplied by the height. This is the change of potential energy of each brick. All right, so now we simply substitute our values. So we have 3 bricks. Each one has a mass of 2 kilograms. Little g is 9.8. And my height is going to be 1.5 meters. All right, that is the amount of work you're going to do. Now you do that and put those numbers in the calculator. You should get approximately 88.2. That's measured in joules right now. Notice it's also the same amount of work you're going to do in this case because I am lifting the 3 bricks from the ground to the tabletop. So again, this is also 88.2 joules of work being done. Now, this is where the power comes in. So power, again, here I'm talking about an average power because I'm just looking at the total time here between these events. So the definition is right up here. It's the total work being done in some amount of time. So here it would be the work divided by delta t. And my delta t here would be my 15 seconds. So here I would do 88.2 divided by 15. Put that in a calculator and I should get something like 5.88 joules per second, which is a watt. That is the average power that this person, right, is doing work. Okay? That's the rate at which he's doing work. Now, how about case number 2? I'm taking longer, right? So I do the same amount of work, 88.2 joules, and I divide that now by 60 seconds. Right? I've changed this amount of energy, but it did it over a longer period of time. So the power is going to be smaller. In this case, I get 1.47 watts. All right, so this is kind of a simple example how you could see how time, work, and power are linked together. All right, I want to now have a look at this instantaneous power and specifically the case where we have constant force. So here's a situation where I would have a constant force. So I have a force here. I've attached a cable to the crate again, except now this force or this cable makes some angle theta with respect to the horizontal. And I'm going to drag this crate here along the floor, a distance or x. So right away, you should be able to calculate how much work is being done by that force. You simply apply our definition, fx cosine of the angle theta. Now remember, how do you define power in this case? Power is the rate at which we do work. That's dw over dt. Now we simply substitute our definition of the work. So here we have fx cosine of the angle theta. Well, now what can I do if I'm taking a derivative of a whole bunch of terms? To make it as simple as possible, I would simply take out all the constant terms. I could take out the force, that's a constant term. The angle theta here is also a constant term, and I'm left with what? Dx over dt. All right, so what is dx over dt? Well, this is simply the x velocity, right? The x component of the velocity. And this crate here is simply moving along the floor here with some velocity in the x direction. So at the end, this instantaneous power, at least when it applies to constant forces, you can often write it like this, as force, velocity, and cos of the angle between that force and the velocity of the object. So power can be written in this form here also, only though in case of constant forces. All right, here's our first problem. We have a skier of mass 70 kilograms is pulled up a slope by a motor-driven cable. First part says how much work is required to pull her a distance of 60 meters up a 30-degree slope at a constant speed of 2 meters per second. And the second part says a motor of what power is required to pull the skier. If you've ever gone skiing, this is what it looks like, just this tow rope here pulling up the skiers up the slope. What I would start first is just to do a kind of just a simple cartoon of what's going on and just define some terms here that we have to work with. So I'm going to highlight, well, we know that they are going up a distance of 60 meters and it's a 30-degree slope. I also know that the speed is constant and that the skier here has a mass of 70 kilograms. All right, if you're not sure how to start a problem like this, again, how much work is being done to pull her up? So I would probably start with a free body diagram on the skier. I have a weight acting down the slope. I have a tension force acting up along the slope, right? I'll just call that tension F. What else? There's no friction here, so what we can then do is just put a normal force over here. The normal force is perpendicular to that slope, and this is what you have. Now, whenever you have an object on a slope like this, it's always a good idea to break that weight down into two components, right? You have a component of the weight that's acting down the slope, and you have a component of the weight that's acting perpendicular to the slope. This guy here is mg cosine of theta, and the one acting down the slope is mg sine of theta, right? That is the weight parallel to the slope. That's important, okay? So one important aspect of this is that you're moving up at constant speed. So what does that mean? That means that the acceleration of the skier is 0, which means that the net force acting on the skier must also be 0. Well, what does that mean in terms of these forces here along the slope direction? That automatically tells me that my force F must be equal to this parallel component of the weight, mg sine of theta. That's the only way you're going to get the acceleration equals to 0. Now, the reason I want to know this, well, I know the mass, I know little g, I know sine of the angle. I could right away, I could calculate this force. But the question is asking me to calculate the work. So how would you do the work? Well, I apply the definition. It's the force multiplied by the distance. Well, the distance that the force is acting is this guy, right? That is my distance x up the slope, which in this case is 60 meters. I'll just write that as x multiplied by cosine of the angle between the force and that displacement. It's actually cosine of 0, so I'm not even going to put that in here. So now if I substitute my force, what do I get? mg sine of theta, all this, that's my force, and multiplied by x. Now all you have to do is substitute the numbers. So the skier is 70, little g is 9.8, sine of 30 degrees, and multiplied now by the distance, which we said was 60 meters. All right, we put all of those numbers in the calculator. You should get something like 20,580. That is measured in joules. All right, question B says, a motor of what power is required to pull the skier? So now we're looking for power. And in this case, the simplest way to do it here is simply to take that force, right, and multiply it by the speed v. Okay? Again, there is no angle here between the force and the speed, so this is a straightforward application. I could also calculate the change of energy of the skier because, look at, here is the height, so I'm changing the potential energy of the skier by this force. Therefore, I can calculate that change in energy, and I can also calculate how much time it takes. And I'm also going to get to the same answer right here. So what are we going to have here? The force is mg sine of 30 degrees, sine of theta, and multiplied by the speed v. Now we just substitute our values. So you get a mass of 70, you get 9.8, sine of 30, and multiplied by the speed, which they've given us here is 2 meters per second. Okay, this power here, put that in the calculator. I think I got something like 686. That is measured in watts. Okay, so that is my power for this problem. All right, I just want to show you that if I do calculate the change of energy, I'm going to get the exact same answer. Let me give myself some space over here. And let's imagine I calculated power this way, right? What is my change in energy? In this case, it's going to be a change of potential energy. And how much time did it take to change that potential energy? So the potential energy change is going to be this. It's going to be mgh and divided by the time that it takes, delta t. Well, how would you write the height here? Let's imagine we did some trigonometry. You can write the height here as being sine of the angle theta is equal to what? H divided by x. Okay, so I can write the height then as being mg x sine of theta rather. Okay, and now I still have to divide by delta t. Now right away you can see if you group together this x and this t, right? X is the total distance, t is the total time. This is the definition of the speed, right? X over t is going to be my 2 meters per second right here. Okay, so the velocity here, since I'm moving up at constant velocity, it's simply x divided by delta t, right? How much time it takes. So right away you can then substitute that into our definition. So you get mg sine of theta. Let me just switch the order, substitute v in here, and that's it. You have the power equation. And this is exactly all of the terms that we have down here. We have the mass, we have little g sine of theta, and multiplied by 2. Right? So you're still going to get my 686 watts, regardless of how you solve this problem. All right, here's our second problem. We have a 650 kg elevator, starts from rest and moves up for 3 seconds with constant acceleration until it reaches its cruising speed of 1.75 meters per second. Part A says, what is the average power of the elevator motor during this period? Part B says, how does this power compare to the motor power when the elevator moves at a constant cruising speed? All right, let's highlight some key terms here. We have 650. This is going on for 3 seconds. We have constant acceleration in this case. And we're going to be eventually moving up at a cruising speed of 1.75. So for part A, I'm going to calculate it 2 ways. So my formula first for average power, again, I'll just write it right here. How much work is being done divided by the total time in which the work is being done. The time is 3 seconds right here. That's delta t. So you're already done with that. Now to calculate the work, we can do 2 different ways. First of all, here's kind of a little sketch of what's going on here with the elevator. And if I start drawing some of the forces here, so I have a tension force, Ft over here, and the weight of everything is going to be the mass of everything multiplied by little g. So 650 times little g, that's it. Now in the first part, what you have to remember here is that we have some acceleration here, and the acceleration is going up, which means that Ft is bigger than mg. So if I apply Newton's second law now, I would say that, well, Ft minus mg equals to ma. All right, and Ft is then bring mg on the other side. What do you get? Ma plus mg. All right, now why do I want to know how big this force is? I could, in principle, I can calculate it, but I need to know what the acceleration is. But that's okay. We know the acceleration is constant. So the acceleration, the definition is simply delta v over delta t. That's v final minus v initial divided by delta t. V final is 1.75, delta t is 3, v initial was 0. So we put that in the calculator, we get an acceleration here of 0.583 meters per second squared. Now I want to know the average power. So again, I need to know what this work is. That's the key. So the work, I could calculate it first just by knowing this, right? The work is going to be my force that being applied, that's my tension force, multiplied by how far am I going up during this first 3 seconds. That is multiplied by some height y. Okay, that's it. So how do I calculate the height y if I'm accelerating? Here we're going to use some kinematic equations. Again, if the motion is constant acceleration, this is how I could calculate how high I'm going to move up during this time period. So you have 1/2, 0.583, and the time is 3, and I have to square that. So I get a displacement in that vertical direction here of approximately 2.62 meters. All right, we're in a position now where we can calculate everything. We know the acceleration, we know little g, we know the mass. This force here, this tension force, is 6,750 newtons if I substitute all the values. So right away, you should be able to plug everything in here. 6,750 multiplied by the distance, 2.62. This gives me a total work here of 17,000, say 700 joules approximately. Now we're looking for the average power. Now you go back to my average power definition, and you can calculate the average power is 17,700, let me try that again, divided by 3 seconds. That's it. All right, so you get approximately, say, 5,900, and that is simply going to be measured in watts. All right, that's the average power of the elevator motor during this period. Now I could have also calculated the work here by noting, well, what's changing over here? I'm changing the energy. I'm changing the kinetic energy, but I'm also changing the gravitational potential energy. All right, if you do that, you're going to get the same value for the work that we calculated here at the 17,700 joules. The approach is different. The change in kinetic energy is 1/2 mv squared. And the change in gravitational potential energy is mgy. But again, I know all the values in here. Just substitute everything in here and you get approximately 17,700 joules. At the end, my power equation is the same. The work is the same. You've just calculated the work slightly differently. All right, now let's go to part B for this problem. All right, part B says, how does this power compare to the motor power when the elevator moves up at constant cruising speed? So that is a key word. That means right away I'm going to get rid of all of this, and the acceleration then is 0 because the speed is constant, the velocity is constant. Well, right away this is pretty straightforward. That means that my tension force in that cable must be equal to the weight if there is no acceleration. And then that means that the work being done by this tension force is simply equal to the force times the distance, right? So here all you would have would be Ft times the distance y that I'm moving up. But all I want to know is the power, right? And my power then is simply the work divided by the time, okay? Again, the work is Ft, y over t. Again, y over t is what we call the vertical velocity, Vy. Vy is this cruising speed here of 1.75. So all we do now is we substitute our values. So you have mg multiplied by Vy, my cruising speed. So my power is going to be, the mass is 650, little g is 9.8, and now my speed is 1.75. All right, we put all of those numbers in the calculator, and you should get 11,150. And again, this is here measured in watts. Okay, so that's the power when you're cruising at constant speed. So it's much higher, right? Again, in the first case, we're looking at the average power over that whole 3 seconds, right? All right, I want to sketch a couple of the quantities here that we looked at for the previous problem, just as a function of time. So I'm plotting before, in the first 3 seconds during that constant acceleration. I want to look at the velocity, the work, and the power as a function of time. So first of all, in the first 3 seconds, remember we had that acceleration, right? We had a constant acceleration, which means that, at 3 seconds, I'm going to hit that cruising speed of 1.75. And before that, I should have like a linear relationship here. And then I'm simply going to be cruising here at 1.75. And again, this is in meters per second, right? That's what the velocity looks like. The slope of this part here is nothing more than the acceleration, right? That's the slope, and I think we had 0.583 meters per second squared. So what would the graph of the work as a function of time look like? Well, again, if you think about the work, it's that constant force, right? That tension force that we calculated, at least in the first part, right? And then what else? Multiplied by the distance y. Now again, I'm trying to plot things as a function of time. Well, the force is constant in that first 3 seconds. We calculated its value. The distance y, I know from kinematics, should look like this, at least in the first 3 seconds, right? This is from time less than or equal to 3 seconds. This is what the relationship should look like. So again, if I make a sketch of this here, I should have a a parabolic relationship here because of this. Now, what happens after 3 seconds? After 3 seconds, it's a different section, right? So what we're going to have here is we actually had a different force, Ft, right? The tension here was only equal to the weight in this case. And the other thing I had was that my distance y then can simply be written as v multiplied by t, and v is that cruising speed. So what you have here is you have a linear relationship over here in this section. Okay, so that here should be a straight line after 3 seconds. So what about power? Well, power, our definition is the rate at which work is being done. So you could right away just differentiate both of those, and what you're going to get for power then is you're going to get a linear relationship here up until 3 seconds. Now once you reach that 3 seconds, again, now you're going to get this constant value right here, but this constant value is down over here. And I'm going to show you this in a second, what this means. So what we calculated here was this power here. Once you're cruising at constant speed, we had 11,150 watts. That was my power. And actually the problem was to calculate the average power. And the average power was somewhere down over here. Remember, my average power here was 5,900 watts, right, approximately. But I didn't calculate the power as a function of time. You could see that the instantaneous power right here, right, whatever that power is here at 3 seconds, it's going to be actually bigger than this guy over here, okay? This wasn't a problem here, but this is what the sketch would look like, okay, as a function of time. All right, here's problem 3. We have a horizontal cable. It accelerates a crate across a frictionless floor. The work done by the cable's force on the package is given by this equation over here, 0.2 multiplied by t squared, where W is measured in joules and T is in seconds. Question A says, what is the average power due to the cable's force in a time interval from 0 to 10 seconds? And question B says, what is the instantaneous power due to the cable's force at this specific time of 3 seconds? And is this power increasing or decreasing with time? All right, so for part A, what we're going to do is calculate the average power. So power, my average here is going to be the work and divided by kind of that time interval that I'm looking at. Well, how much work is done in the first 10 seconds? Well, all you would really have to do here is do what? Well, simply we have an equation here for work as a function of time. So that's it. You simply do 0.2 multiplied by t squared and then divided by that time interval, which is 10. All right, you can cancel this out, and what you're left with here is 0.2 times 10, which gives me 2. That is 2 watts. All right, that's it for that case right there. That's pretty straightforward. What about B? It says, what is the instantaneous power, P ints, due to the cable's force at this specific time? Well, how would we get power, the instantaneous power? The instantaneous power is the rate at which work is done. That means you have to differentiate the work with respect to time. That is a pretty straightforward one, right? You take the derivative of 0.2 t squared, should give me 0.4 multiplied by t. All right, and now they want you to evaluate this at exactly 3 seconds. So all you do in that case is you substitute the 3 seconds inside here, and what you get here is 1.2 watts. All right, that's it. And is it increasing or decreasing? Well, have a look at my equation, right? My equation is like this. It's 0.5 times t. As I make t bigger, I'm going to increase that power. It's a good idea to try to make a sketch of what everything looks like right here. So let's go see. What if we had a sketch of the power as a function of time? Power as a function of time is this linear function, and I'm going to go all the way to 10 seconds. So this is time, and this is going to be my instantaneous power. What I have here is I simply have a straight line. And the slope of that line here is 0.4. That's the number in front of the t. So in the first case, what I evaluated was this P average, and I got a value of 2 watts. And here I'm evaluating at this specific time of 3 seconds, and I get 1.2 watts. So over this whole time interval, so I started over here at a power which was equal to 0. At time 0, I have 0 watts. What do I have actually at time equals to 10 seconds? So you have to substitute 10 inside my equation here, and what you end up getting here is 4 watts. So what does the average represent? The average represents all of these values, and since it's a linear, the average represents this, exactly the halfway point between the minimum and the maximum. Right? Another way you can calculate my average power over a time interval, if the relationship is linear, it's simply to take this, Pi plus P final divided by 2. Right here you would simply get 0 plus 4 divided by 2. I'd get 2 watts to be my average power. That 1.2 watts that we calculated for part B right here, well, that's because we're over here at 3 seconds. At 3 seconds, we're less than 2 watts, okay? So we're at a value here of 1.2 watts. So this is what it would look like here on a power versus time plot. All right, folks, that's it for me. Hopefully you appreciated this video on power and it helps you to solve your problems dealing with work and power. We'll see you next time.